have the pleasure to introduce the talk by Catarina Moreira. She will tell something interesting about quantum-like influence diagrams and their applications. Please.
Hello, good afternoon. Today I will be talking about quantum-like influence diagrams, but in order to... First of all, I want to stress this is just a preliminary study, something that I am still thinking about it. Before talking about influence diagrams, I have to talk about something fundamental, which is Bayesian networks. And before talking about Bayesian networks, we need to understand what is the motivation of this work. So this work is a complement from yesterday's session about quantum cognition. So usually people do not follow the rules of probability theory while making decisions under uncertainty. And one of the consequences is the violation of the sure thing principle. So for instance, let's imagine that if I win the lottery, I will buy a car. Let's also imagine that I really need the car, so if I lose the lottery, I will also buy it. But if I do not know the outcome of the lottery, the logical assumption is, well, if I know that I won the lottery, I will buy the car. If I do not won the lottery, I will buy it anyway. So supposedly I should choose to buy a car. But what happens is that people choose under uncertainty, people choose other actions. And this is basically the violation to the sure thing principle. One of the examples of the literature that is highly cited about this issue is the prisoner's dilemma game, an experiment performed by Shafir and Tversky in 1992. So we have the same situation. So in the prisoner's dilemma, we have two people which are in separate confinements, and they committed a crime, the player is informed if the other has chose to defect. So they say, what will you choose if knowing that your friend chose to defect? And in the other situation, he was asked, okay, your friend chose to cooperate, what will be your action? And in the third condition, the player did not know the outcome of the other player, and he was asked what action he will perform. So, of course, when the player knew that the other one had chose to defect, the best option should also be to defect. So 97% of the people chose to defect. When they knew that the other one chose to collaborate, then the best choice would be also to defect, because he would be set free. So, under the sure thing principle, the right action would be, if I do not know the outcome of the other player, I should also choose to defect. But what happens is that we have a decrease of the number of people who actually chose to defect. So people tended to be more cooperative, and this violates the sure thing principle. And many experiments in the literature replicated this. So it is not a singular experiment, it's something that actually occurred. So during my PhD, I worked with the violations of the sure thing principle. And one of my concerns is that many of the models proposed in the literature work in very small decision scenarios, like the prisoner's dilemma game. So I wanted to figure out if there would be a model that could be general enough to represent complex decision scenarios. And one of the ideas would be Bayesian networks. So Bayesian networks are probabilistic graphical models. They are acyclical graphical structures in which each node represents a random variable, and each edge represents an influence from a source node to a target node. And each random variable is followed by a conditional probability table which specifies the probability distribution of that node according to its parent node. And Bayesian networks are highly powerful structures. For instance, let's say, and they can be applied in several different decision scenarios. Take, for example, a medical decision scenario where I have a lung disease which has several random variables, either a person smokes or not, can influence the presence of a lung disease, and several symptoms would be the shortness of breath, chest pain, and so on. And the good thing about Bayesian networks is that I can ask them questions. I can ask, if a person enters in my office, what is the probability of him having a lung disease? And I would know that it would be 2%. And I would also know that a probability of him smoking would be 20%. Another good thing about Bayesian networks is that they allow me to observe people and to provide pieces of evidence. If a person comes to me and he says, look, I'm a smoker and I have a shortness in breath, I as a doctor can say, well, then you have like more or less 70% probability of having a lung disease, because there were evidences that may increase this probability. So in a Bayesian network, I have query variables, the one that I'm asking the question. I have observable variables, the ones that I provide a piece of evidence, and I have unobserved variables, which are uncertainty. I don't know regarding the decision scenario. And there are two major steps to compute a Bayesian network. So you first need to specify a full joint probability distribution, which is nothing more than the multiplication of the probabilities of all nodes. And you need to make a marginalization, which is basically when you make a question. You sum out all the variables that satisfy the conditions of your question. And then in the end, we need to normalize the K2-based assumption. However, these Bayesian networks are, the underlying aspect is classical theory. So they cannot make an explanation for the violations of the short-think principle under the present Darwin again, for instance. So, is it possible to extend these Bayesian networks in a non-classical probability way in order to explain violations to the short-think principle? And the question started in Feynman's path diagrams, for instance. So, if I have that, and this is going to be the underlying, the heart of quantum cognition. So, if I have a graph, the probability, the classical probability of going from A to D, so I want to make the probability of A to D, in a classical setting would be going through this path here, which I will call path 1, or, so it's going to be path 1, or going through the second path, going through this path here, which I will call path 2. This will be the classical setting. If we, instead of using real numbers, we use complex amplitudes, then things change. Because there is a rule, which is Born's rule, which says that the conversion of a quantum probability amplitude into a probability value is performed by making the squared magnitude of the probability amplitude. And by making let's put here, an amplitude is represented by complex numbers, so path 2. By making this operation, I automatically get something very interesting, which is a classical component and a quantum interference term. And this is the heart of quantum cognition, because it is through that quantum interference term that I will be able to model violations to the short-think principle. So, and this is perfect, because Bayesian networks allow me to not have observed variables. I can have unobserved variables, which can enter into superposition and produce these quantum interference effects. If I observed these nodes, then it would collapse to classical theory. It's just like the double-slit experiment. So this is the underlying aspect of the quantum-like Bayesian network. Just replacing real numbers by complex numbers and just let the mathematical consequences emerge. So how do we do this? It's exactly the same. I just apply the Born's rule to the quantum probability amplitudes, and I automatically get a term which is the classical probability plus an interference term that is general. It is not just for 2 random variables, but it can work with n random variables. Maybe they can't. Can you hear me? Okay. So, of course, we have a problem. This quantum interference formula will generate an exponential amount of quantum interference terms. And so far, the literature usually tries to overcome this problem of setting the interference term. Mostly they just look at the outcome of the experiment and they set these parameters. There are, in the literature, Yukalov's model with Professor Sonnet, which made an heuristic to set these quantum interference terms based on the quarter law of interference. But it's a static thing, and if we try to map it for n random variables, maybe it's not the best choice to fix it to a value. Maybe it's better having something dynamical. And as you can see, these interference terms can be almost anything given in some range. So how to choose the right ones? So I also went to a similar approach and developed an heuristic, which basically takes into account the marginal probability distributions and computes the inner product between them in order to set dynamically these quantum interference terms. So the underlying idea is that I grab the full joint probability distribution. When I make a query, I have to extract their marginals. And by making their marginals, I can compute inner products that can set the quantum interference terms. And I also came up with a similarity measure, which basically says how similar these marginals are and how these inner products between them are. And for the sure thing principle, I came up, after analyzing several results from several different experimental findings, I came up with this general formula. And after testing it for a quantum-like Bayesian network for the prisoner's dilemma, for instance, we showed that the predictions the errors were very, very low without, this is just a predictive model. I didn't go to the experimental outcome and set it manually. And in another range of experiments, low errors again. Same heuristic for the two-stage gambling game. It worked. And now what's the problem? Okay, I tested this for small decision scenarios, but this is not what the model is for. It should be applied for large-scale, real-world scenarios. So I also decided to apply this model in a financial problem. For instance, let's imagine that the company lost its data. Let's also imagine that, it's not imagined because it's really true, companies don't know what their employees are doing. The only thing they have is textual records of the tasks that have been conducted. And so we had this problem of business process management, in which the only thing we had was textual evidences of the tasks of the company was doing, and the goal is to determine what was the workflow of the tasks being conducted in the company. So we analyzed a financial textual data from a financial institute in the Netherlands. And of course, this was the first thing that I got. It was intractable, it was unreadable, it was everything. So I decided to analyze a little bit better. The company had computer automatic tasks and tasks conducted by people. And of course, people make lots of errors. So as you can see, there are transitions between tasks with very, very, very small probability of occurrence. So probably people made mistakes and those transitions should not happen. So I eliminated several of these rare events. I also determined several cyclic tasks, redundant tasks that could be collapsed to a single one. So I am even optimizing more the workflow of the company, and you will see later why this is important. So after having everything cleaned, I came up with this Bayesian network, which is representative of the workflow. So basically the idea is that a person would ask for some credits, then some computer tasks would occur, and then some people would have to evaluate if the credit was eligible or not. And what is interesting is that if I observe that the credit was approved, I automatically know the full process, what tasks have been conducted in a company. But this is very, very interesting. But this is what the full data. Now, what happens if I lose the data of the company? If I don't have all this information, will I be able to extract the same model? I made a decision model that learned from the textual evidences. As you can see, it's 50%. So it's total uncertainty. There wasn't enough data for the model to make decisions. So, is there an opportunity for the quantum model to overcome this? And basically, yes. What happens, the quantum, we have the classical model, and what the quantum model is, it provides a parametric layer corresponding to the quantum interference effects that can disturb these probabilities. So by disturbing these probabilities, I could somehow correct them. And I didn't do this manually. It's impossible. I had 6 million parameters in there. It was impossible to do it manually. So again, I had to look for the spread of the data and refine the little bit that heuristic that I proposed before. So the quantum-like Bayesian network for missing information was able to have an 8% error towards the classical one, which had 25 or 23%. But this is very interesting. Okay, we are dealing with probability distributions, but what I really wanted to propose, and this is something that I'm still thinking, so any discussions would be interesting to help me on this, is, okay, I don't want a probability distribution. I want to act upon it. If I'm a doctor, it doesn't matter if there's a 70% probability of a person having a disease. I need to know how to act towards that information. So, is it possible to extend these quantum-like Bayesian networks and incorporate utility theory on them? And my answer is yes. There is this structure called influence diagrams that had its use in the 80s. I'm not sure why they stopped being so used nowadays. But it's interesting because we can use the knowledge representation of the decision scenario of the Bayesian network and make it influence the utility function. The final probabilities of the utility function. So, going more deeply, an influence diagram has 3 components. One of them is random variables. In this case, I will use the quantum-like Bayesian network, which can provide the interference effects. It has a decision node. For instance, for the prisoner's dilemma game, I need to know if I will play or if I will defect or cooperate. And then I have an utility function which says how good are my preferences, which can be seen, for instance, as the payoff matrix, my adaptation of a payoff matrix of the prisoner's dilemma. And the goal is from a set of actions, I want to choose the action that provides me the best utility. So, of course, when we specify this using quantum probability amplitudes, we have to use Born's rule to convert to probabilities. So, interference effects will emerge. And this is just a simplification of the formula. No? So, how can we apply this? So, this is something that I'm still working on, a preliminary idea. So, how can this be applied in a decision scenario like the prisoner's dilemma game? So, I thought a lot about it, and in order to have some interference effects, I would have to put some context of the decision scenario. So I have a player in a separate confinement with some personality, which can be risk-seeking or risk-averse. If he is risk-seeking, the probability actually it should be the other way around. If he's risk-averse, he should defect more, but it's just whatever. So there's the conditional probability distribution of player 1 towards its personality. And then I'm player 2. I'm in a separate confinement, and I want to make a decision towards this. And I have my payoff matrix. I put negative terms because I want to maximize the expected utility. The underlying idea is that I will make a joint probability distribution of my utility term using the full joint probability distribution of the Bayesian network. And I would basically, so that strange formula will basically be all the combinations, so the full joint probability distribution of the network times my utility. So this would be, if I prefer to make a defection, And this would be if I would decide to make a cooperation, so that the utility terms change.
Excuse me, where do you get the 0.97, 0.03?
That comes from the specification of the Bayesian network. They're the conditional probability tables, which are represented by complex numbers. And then when we try to make a decision towards, okay, what's the utility of defecting, given that I suppose that P1 would choose to defect, then I can make a marginalization, which will again lead me to a quantum interference term. And again, I have the freedom of a whole set of possibilities. So I can either choose to favor a defection action or a cooperation action. And this cooperation action is actually what occurs in the violations of the sure thing principle. So I can basically find a set of parameters that will make my cooperate utility higher than the defection utility. But again, this is still something that I'm working on. It's still very formalized. It's just an idea that I would really like to explore, because this is the underlying heart of quantum cognition. Is this free? It is these free parameters that allow me to give more freedom in modeling. And why not apply it? And why not allow a quantum-like Bayesian network influence my utility function? It's just something that I would think about. So, summarizing, we have seen that quantum-like probabilities use non-commutative models, are also predictive models using a similarity heuristic function that are developed. They show that they can deal with violations of the sure thing principle. They also show that they can be applied to real-world financial scenarios, and so far, to the best of our knowledge, this is probably the first work that has been conducted using quantum-like models towards real situations. So there, of course, this can have some implications, because this additional layer that we use, it can, if we analyze it more deeply, we would have to try to understand if it's overfitting the data, because there is a lot of relation between this parametric layer and machine learning. So what is machine learning? It's simply also a set of parameters that I need to tune using the data that I have. And it's basically what I did, but in a very relaxed fashion. Also, influence diagrams, they are designed for knowledge representation. So I can visually, they have an elegant visual representation of the decision, and they can represent the full probabilistic description of a decision problem using probabilistic inferences. The problem is if I use classical influence diagrams, I will not be able to explain several paradoxical findings of the literature, because classical theory follows the normative analysis, so it tells people what they must choose in order to have the higher utility. But what we have seen so far is that we need models that tell us how people actually choose and know what they must choose. So, thank you very much.
Your presentation, particularly because one of the authors of the paper mentioned, so we have time for a couple of short questions. Of course, by consistency.
I'm interested, so can you go back to the prisoner dilemma rather than the slide where you showed that you have been able to actually try to convince people to cooperate, right? Because you get the final utility function, not after the one where you give the result 44 against 40. So, of course, this assumes a certain distribution of the angles.
Yes.
But not the exception.
Yes.
So you cook up the result.
Exactly. Yes. That's not. Basically, we are cooking in.
But is it? Can you justify? I mean, is there a psychological framing, or could there be a theory behind this underlying distribution of the data?
Well, my idea was that what I still want to explore is that probably in the decision scenario, in the Bayesian network, so if I'm in a separate, there are two players, I have another one I have one player in a separate confinement, and in my thoughts, if I'm reasoning about whether I have to defect or cooperate, I have to take into attention if the guy on the other side is risk-seeking or risk-averse. I have to take into account his playing personality. So I think having into account these additional random variables can give some underlying intuition of which direction of the spread of the data then for the tethers will be. But this is still something that I'm thinking. I'm still not very... I just finished last night trying to come up with the simulations, but yes, that is very... It requires a formalization in the implementation, of course.
I think this is kind of interesting, but I have problems with prisoners dilemma because it does not seem to be valid in the real world. It's highly replicable in the laboratory.
Exactly.
But there are a couple of problems. First off, the scientist often chooses values to make cooperation better than, more valuable than competition, which is in our place. And the second thing is that personality, you call them risk seekers versus risk averse people. The personality replication or validation is very cool. So there are lots of problems with it. You might, one of the things that Wittig talked about is getting data from quantum simulation. You might look more favorably in that area. I'm not sure that this is really.
Yes, I totally agree with you, and I can even give you two explanations. First, my goal with this model is to, again, like I started in my PhD modeling these very small decision scenarios and then going towards the real data. So in here I'm also trying to make some first steps in order to try to extend the quantum Bayesian networks to incorporate utility functions. The thing is that in a prisoner's dilemma you usually model it with two random variables, one for one player and one for another. But I will not get interference effects like that, because in influence diagrams, I will only have a decision maker, and then I have the context of the decision scenario, which includes the other player. And like that, I could not produce interference effects. So I just put the personality as a toy example of how this model would behave and how the interference effects would occur. But yes, yours. Totally right. Yes.
Yeah, Eisen's work gets to a solution faster than the classical prisoners pool game, but gets to the same solution. So,
yes.
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 Thank you.
Let's thank the speaker.